Gerry and this is my Stirling engine. Now I'm going to explain to you how this engine works, but before I get into the physics, I'll explain to you the design. The first step is this ring stand. This ring stand holds the whole apparatus a couple inches off the table so that you can put a candle underneath. The next step is the cylinder. The cylinder, as you can see right here, is actually made out of two separate cans. The top half being made out of a Coke can, and the bottom half being made out of a tin can. And you attach them right about at this point using RTV red silicone. But for now, we'll just treat them as one object, the cylinder. The next piece is the displacer. The displacer is also made out of two separate cans. Two Coors Light cans to be exact, and it is the bottom piece of both cans. And the reason we use these Coors Light cans is because they're the perfect size to slide up and down within the cylinder, allowing some air to move around the sides, but not too big to have friction with the walls of the cylinder. The next piece is a PVC pipe that extends out the side of the engine, and then there is a balloon on top of that. And there's a hole here so that air can flow freely from inside the cylinder into the pipe and into the balloon. Next piece then is you have crankshaft supports that extend upwards, and then you have a crankshaft that extends across the crankshaft supports. Now, there's also a flywheel here that is a CD, and I used a cork, as you can see on mine right here, to hold the CD in place. There's also a needle that goes from the displacer through the top of the cylinder, and then there's a wire that goes from that needle. You wrap it around, and then it goes up to the crankshaft. And there's also another wire that you super glue to this balloon, and it goes up to the crankshaft. And so the net effect now is that when this flywheel spins, this displacer will be moved up and down within the cylinder, and this balloon, when it inflates up and down, will move this wire up and down, which will turn this crankshaft. So it is the balloon that actually makes this whole situation run. So that is the basic design, and now I'll explain the physics. I'll explain the physics behind the Stirling engine. The main energy source is a candle underneath that provides heat. This creates hot air underneath. There's also ice on top that provides cold air. Now, the hot air, to start the apparatus, you have to spin the flywheel. This then turns the crankshaft and forces the displacer down. When the displacer moves down, this hot air gets forced up around the sides of the displacer, and then it goes into the pipe and into the balloon. Once it goes into the balloon, it inflates this balloon, which then moves this wire up and then turns this crankshaft. As it turns the crankshaft, it then pulls the displacer back up to the top, and then the cold air from the top gets forced down. Now this cold air gets heated up by the candle, and then as the crankshaft continues to turn, it gets forced back up into the balloon and turns the crankshaft. So as you can see, it creates a cycle where the hot air just keeps rising and the cold air keeps going down, and this keeps inflating the balloon. It keeps continuing to turn the crankshaft, and as long as you have a candle underneath and ice on top, this cycle will continue indefinitely. And this is a clip of my Stirling engine working.
Bam. God damn! Look at that! Yeah!
Alright!
I spun it the wrong way.
Look at this.
That thing's wrong.
Wow.
And this is a graph that I've made of the motion of the flywheel on the Stirling engine. To create this graph, I used video analysis on Logger Pro, and then I continuously clicked one part of the flywheel as it rotated. As you can see, the Y position, which is represented by the blue dots, moves in a sinusoidal motion. Now, to calculate the RPMs, what you'd like to pay attention to is the B, which is equal to 17.16, that is shown at the bottom of the picture. So now that I've found the B to be equal to 17.16, I can use this number to calculate the period. Now the period, T, is equal to 2 pi over B. Using a calculator, I found this is equal to 0.3661528. Now this tells me how many seconds it takes to create to do one revolution. So to figure out the RPMs, you just set up a quick portion. So and we find that the X, which is the RPMs, is equal to approximately 164 rotations per minute. Interesting thing about that is a CD reads at 200 RPMs at the center. So as you can see, I was able to actually create a Stirling engine that rotated relatively quickly. At the center, it rotates almost as quickly as a CD reads at the center. So that is my Stirling engine project. Special thanks to Jimmy and Luke for helping me build it. Special thanks to Dr. Fillar for teaching me this material, and special thanks to Mazen, Donnie, and Joe for helping me film this video. So that's my Stirling engine video.